So I want to tell you about indeterminate structures. A structure is indeterminate if the equations of static equilibrium aren't good enough to solve for the unknown reactions. I'll start off by telling you about a statically indeterminate continuous beam. So let's just say that we have, for example, two or more spans. I want to tell you about the three-moment equation, which is a formula for calculating the unknown reactions for such a beam. Okay, so I want to tell you about the three-moment equation for analyzing an indeterminate beam. Okay, so notice this continuous beam I have here. Okay, I didn't put any loads on it, but when I do an example, I'll throw a load on there. We use the three-moment equation, analyze two spans at a time. So I've got two spans here between A and B and between B and C. Sit here at joint B, I say sit here. Sit at joint B, the left span is AB, the right span is BC. The length of the left span, L sub A, the length of the right span, L sub B. Obviously, I cannot determine the three unknown reactions using the equations of equilibrium. Okay, so here is the three-moment equation. Some books cover this, others do not, but I want you to say you've heard of it. This assumes that the cross-section is uniform throughout. If I have a different moment of inertia in AB versus BC, then the formula gets more complicated. But I'll assume constant cross-section. So it's m sub A, L sub A, plus 2m sub B, L sub A plus L sub B, plus m sub C times L sub B is equal to negative 6 times this quantity you see in parentheses. Okay, anything that's capital M means the moment. So moment at A, moment at B, moment at C. The lengths are self-explanatory, L sub A, L sub B. Okay, so what is this? A sub A times A sub B times B. Okay, what are those? A sub A is the area of the moment diagram between A and B. If you put a load on here, there'll be some kind of moment that's generated in that span. A moment that's generated, you can create a moment diagram based on that. And then you can calculate the location of the centroid of that moment diagram. Little a would be the distance from the left support to the centroid of that moment diagram. A sub B is the area of the moment diagram between B and C. Okay, so if you throw a load on there, it would generate a moment diagram for BC. A sub B would be the area of that moment diagram. Little b is the distance from the right support, C, to the centroid of that moment diagram. The moment diagram between B and C. Okay, so for purposes of this introductory lesson, I'll take this to be my three-moment equation. If I have more than just two spans, well, then I have to do more than just one iteration because we analyze two spans at a time. AA and AB are called the first moments of the areas. So these are some cookbook formulas for standard loading scenarios. So first, this case. Picture a load P that's on a simply supported beam, x sub 1 from the left and x sub 2 from the right. Okay, so I'd have a first moment of the area given by this formula. Okay, first moment of area given by this formula for AB. Okay, now here's another common scenario. Distributed load, omega or W. So the first moment of the area would be, for both cases, AA and AB, 1/24th WL to the 4th. So I have a feeling that I might be using these standard formulas. So for example, calculate the support reactions. Obviously this is indeterminate. I can't use the equations of equilibrium to determine R sub A, R sub B, and R sub C, I mean. Okay, so what's P? P is 15 kips, that's the load. Okay, L sub A, that's the length of this first span between A and B. And I just noticed I forgot to label these nodes. So this is C, this is point B, and over here this is point A. Okay, now it looks better. Okay, so L sub A is 30, L sub B also 30. Okay, why do I say M sub A is 0? The load is over here. Remember that we're pretending that these are standalone, simply supported. Okay, so at A, there's no load on AB, so the moment at A is 0. Okay, actually it would be 0 even if it weren't standalone, because I've got a pin here, so that can't support any moment. And similarly at point C, no moment there, because it's got a roller support. So A sub A is 0. Well, what was A sub A again? That was the area of the moment diagram between A and B. Okay, so between A and B. Between A and B, there are no loads. So that means that A sub A is 0. No moment diagram. No loads, therefore no moment diagram. Therefore A sub A is 0. A is 0. Little a is 0. Okay, if I had some point load on here, for example, that would generate a moment diagram. That would generate a moment diagram for AB, and then I'd have to calculate the distance between big A and the centroid of that moment diagram. But there is no load on AB, so little a is 0. Little b, that's not 0 though, because for segment BC, I've got a load on there, meaning that if I were to model this as a standalone simply supported beam, it would have a moment diagram. That moment diagram would have a centroid. The distance from that centroid to the point C, the right support, would be whatever little b is. I don't know what it is. I didn't calculate it, but it's not 0. M sub b will be unknown. What's M sub b? The moment at joint B. So M sub b is unknown. I should say 1/6 p x sub 2 times L squared minus x sub 2 squared. So I'm going to use this formula to calculate big A times little b. Okay, so that's what I'm doing down here. 1/6 times p times x sub 2, that's this distance here, times 30 squared minus 20 squared. 30, that's the length of the span between B and C. Minus 20 squared. Okay, 20, that's that distance from the right support to the load, P. Okay, so 25,000 kips times cubic feet. Okay, so I believe I have all the information I need to stick into the formula. Okay, so here's the 3-moment equation from earlier. You see I have it up here at the top. Now, I established that some of these were 0, didn't I? So I think I said previously that M sub A is 0. So M sub A, this goes to 0. Okay, and then M sub C was 0. Okay, so those go to 0. And then on the right side, the A sub A was 0, so was the little a, so this term is going to go to 0. Okay, so it simplifies. So 2M sub B, that's what you see here. L sub A plus L sub B. Okay, so those were both 30 feet. L sub A and L sub B. Remember this? Okay, so L sub A, that's this length, 30 feet. L sub B is this length. It's also 30 feet. The apostrophe means feet. 30 feet plus 30 feet is equal to -6. Okay, you see here I've got A sub B times B. I calculated that a moment ago. Remember this? That's 25,000 kips times cubic feet. Down here at the bottom. Okay, so put that in here. The denominator, L sub B, that's 30 feet. Okay, so this equation simplifies to this. Make sure you know how the units work out. So one of these feet will cancel one of these, so it'll be kips times square foot. On the left side, here I'll have feet. The moment will be kips times feet, so I'll have kips times square feet on the left. Okay, so I didn't bother showing units here, but remember how the units work out. So M sub B is 41 2/3 kip foot. Okay, so this is a relevant answer. Okay, the moment at B, where am I? Remember this, the original structure? I've got an internal bending moment of 41 2/3 kip foot. Okay, well, what does that have to do with finding those 3 reactions? I want to find R sub A, R sub B, R sub C. Okay, so remember that number, 41 2/3 kip foot. Okay, so now that I know what the moment at B is, I can analyze the span BC. Okay, so the span BC, where is that? Okay, remember the original beam here. I'm analyzing the span BC. Okay, so analyze a little portion of the beam above point B, and then analyze segment BC. So that's what I'm doing here. I'm analyzing a tiny portion of the beam at B, and then I've got the rest of it BC. Okay, remember M sub B, I calculated that a moment ago. It was 41.6 with a 6 repeats. 41 2/3 kip foot. Okay, equal and opposite. So here, if it's clockwise, here it'll be counterclockwise. So analyze BC. I know what M sub B is. It's 41 2/3. I've got the 15 kip load. I want to find R sub C. So consider the equilibrium about point O. That's where I cut it at B. Okay, so negative m sub b, so that'll be this m sub b, minus 15 times 10, so it's this 15 times moment arm 10, plus r sub c times 30, so it's the unknown reaction r sub c times moment arm 30 is equal to 0. Okay, so do some arithmetic here. And you'll find that the reaction at C is 3.61 kips. Well, now that I know what R sub C is, I can go back to my original drawing. You see here. So R sub C, what did I say that was? 3.61? And then I'll put a box around it so that I know that I had to come up with that. It wasn't given. Okay, and that's kips. Okay, so actually that 1 is repeating, so I'll put a repeater bar above the 1. So 3.61 kips, the reaction at C. So now I can calculate what R sub A and R sub B will be. I can now calculate R sub A and R sub B using the regular old equilibrium equations that you're used to working with. Okay, so you got that? R sub C is 3.61. I calculated that using the 3-moment equation. Okay, so to calculate the unknown reactions at A and B, take the sum of the moments about point A. Okay, so that's what I'm doing here. Consider the whole beam, I say. The sum of the moments about point A is 0. R sub B times 30. So R sub B is right here, times moment arm 30. Minus 15 times 40. So that's this 15 kip times moment arm 40. Plus 3.61 times 60. So that's that reaction at C that I just found using the 3-moment equation. R sub C times 60, the entire length of the beam. Okay, so I find that the reaction at B is 12.7 with a 7 repeats. Okay, 12.7. Okay, I can write that in here. Okay, so now I can obviously determine R sub A by taking equilibrium in the y direction. So that's what I'm doing here. R sub A plus the 12.7 that I just found, minus the 15 kip load going down, plus 3.61. I find that R sub A is actually going down. 1.38 where the 8 repeats. Okay, so here I'll have negative 1.38. Okay, so this indeterminate beam, using the 3-moment equation, I was able to determine the 3 unknown reactions. So there you have it. And now if I have more than just 2 spans, in this case I had only 2 spans, if I have more than 2 spans, then I can only consider 2 spans at a time. Only 2 spans at a time. So if there was another span over here, I'd have to go through this iteration again, considering span BC and then CD. In this case, I only had 2 spans, so it made it easier.